Rohan Holmes from ANSTO Synroc. So today I'll give a bit of an update on where we are with the Synroc waste treatment facility at ANSTO, or the SIMO facility. So I think the last conference there was a little bit of an update of where things are. We've moved on a little bit beyond then, so we'll just start to start to look through that. But I thought, starting out, maybe what are the objectives of this project or the facility that's being developed? And I guess one of the key aspects is to have an industrially relevant demonstration of the Synroc technology. So the Synroc technology itself is for the immobilisation of wastes arising from any sort of nuclear activity. At ANSTO, we produce a lot of radiopharmaceutical, and what we're dealing with is some intermediate level liquid waste that's produced from that process, and we're using the facility to immobilise that material. And I guess one of the other exciting and important parts of the project is ANSTO is the design authority on this project. We're responsible for all of the engineering, so we're developing a good team around the technology for engineering implementation. So on that note, I just thought I'd put this slide up here. It gives you an idea. There's a fairly large team involved in this. So ranging from engineers, contractors, fitters, safety personnel, the operational readiness team. There's a fairly large project, a team sitting behind the project, with us all working together to bring this first-of-a-kind technology, or to deliver this first-of-a-kind technology. So I'm sure I've missed a lot of people in there, but it just gives you a feel for the size of the project. So starting out, looking at where we started, well, the process itself of making the Moly-99, we have target plates that are irradiated in opal. Those plates are taken to the A&M facility where the Moly-99 is extracted. Some waste streams that come from that. We're particularly interested in the waste stream that comes from the dissolution process, which is mainly sodium and aluminium with a lot of fission product. And the main fission product of interest is really Cesium-137. So that gives you a little bit of an idea of the material that we're dealing with. So what do we need to do? We need to take that liquid waste. We need to somehow transform that into a solid material and into a solid, durable waste form. And that's what the process is designed around. And you can see we have our facility in the middle there, which is progressing reasonably well. In terms of design basis for the facility, we're looking at, we had a design basis to treat about 6,500 litres of waste per year. That is a mixture of current production waste, but also from some of the legacy wastes that are on site that also need to be disposed of or made safe. We need to make a waste form that's acceptable to go into some sort of long-term storage, interim storage, or disposal facility. So it's a little bit of a challenge because some of the requirements around that material is a little bit unknown, but we have a high-performing material. We benchmark our materials against international standards for, say, glasses and other materials, and we're well within those ranges for things like leachability testing. So we're pretty confident that that material, well, very confident that material will be disposable. A key driver is designing a facility that's safe, reliable, and maintainable. And that's, I guess, one of the big challenges with this process or the project that we're doing, is doing the design work to ensure that we can not only operate the facility, we can maintain and keep that facility operating. We use nuclear automation where possible, and there's a fairly substantial degree of automation in the process that we'll have a look at later on. Automation's relatively easy. What makes it hard is when you're trying to do it in a nuclear environment. So some of the easy wins that you have with other types of automation aren't available to you in that in that environment. So a little bit of history, a little bit of background on Synroc. It's been around a long time. So, and there's a pretty substantial body of knowledge and literature that's been developed around that material, and the materials are all different types of waste forms. But the research and development's really been driven into the waste form science. So, and there's a history of developing waste forms for challenging wastes, looking at things like reprocessed fuel waste or some of the plutonium or actinide materials, so there's a history in that. But we have a pretty broad range of waste forms available to us, so we can select the waste form that's most suited to the chemistry of the waste and then develop the process around that. I think, and I touched on this earlier, but one of the key things is ensuring we have the required data and models to demonstrate the waste form performance for that final disposition of the material, and that's another key aspect of the work we do. SIMO being one of our biggest project that we're doing, but we still have a lot of other engagements around the world that are also still ongoing, with the UK in plutonium disposition. We just finished our first major report for terrestrial energy in Canada, looking at the feasibility of the Synroc technology for wastes arising from their reactor designs. So we submitted that report just before Christmas, and fairly well received by terrestrial energy. So what's the advantage of Synroc, or why Synroc? Number one, it's durability of the waste form. For this particular application, where we're dealing with the moly wastes, we actually do get a volume reduction as well. So if we had 5 cubic metres coming out of 5 cubic metres, we'll probably have 2.5 or 2.6 cubic metres of waste form produced. So it's a durable waste form with the required performance characteristics. So I guess that demonstrates the advantage of the process. Other technologies are available, but they have their own challenges and limitations. So stepping back and thinking about the process itself, and this is I guess a very simplified overview of how the process operates. We take the liquid waste, we add our waste forming additives to it, so they're the materials that give the waste form the right chemistry and composition. We process that material into a powder through evaporation and calcination. We dispense that into a HIP canister, and then we evacuate and seal that canister and hot isostatically press that material. So the hot isostatic press allows you to put pressure on the can, so you get the collapse of the can and you get the formation of the required waste form. And it's a substantial advantage using this process because all your high temperature processing steps take place in the can itself. So some of the challenges you might have from other technologies with volatilization of radionuclides are much less of a problem with this technology. So your supporting services and systems such as off-gases become much more manageable and simple compared with, say, a vitrification plant or other plants. So what we had some pretty good waste form technology, a bit of an idea of how to process that into a waste form of value. What we really had to get in and do and apply effort to was the technology and engineering development for that, to turn it into an actual, a real industrial process. So I guess when I started the project, we were probably sitting in that 3 to 4 TRL range. And everything we've been doing since then has been driving up that maturation pathway to try and get us, we want to get out to the 9. That takes us a long time, that's operations. But we'll step through some of the work that we've done to get to where we are now. We're pushing that 6 or 7 level at the moment with what we're doing. Once we get the facility, the process installed within the facility and get into the commissioning phases, we're starting to push up that scale again. One of the key pieces of infrastructure that we developed as part of this work, and it's quite nice that Adie's here because he's been a strong supporter of the project and supported even the implementation of the demonstration plant. But we built an inactive demonstration facility, and this was to basically demonstrate the process technology, understand how to integrate the process technology, and then how to operate the process itself. This is all part of driving that technical maturity up. The equipment you see in the facility is the same as what you would see in the final facility. Now, we've only focused on certain parts of the process. We've focused on the parts of the process that had the biggest risk profiles. So what you see there is a lot of the powder production system. So that was early on one of the most challenging and problematic parts of the design. So just a little bit of an overview of some of the things we've been looking at: process integration, validating our process chemistry, our process mass and energy balance, but also how do we decontaminate and clean this facility. We don't want to generate secondary wastes, so we need any liquid we use to decontaminate or clean the process needs to go back in and go into a waste form. So in that facility, we've used that to design a lot of the processing, or the process design, but also the operational parameters for that piece of technology. Spoke earlier about the hot isostatic press. So hot isostatic pressing is something that we've been doing at ANSTO for 30, 35 years. But what we need to do is, we know we need to get to a waste form. We need to get to a waste form with certain properties. And that's what you see on the very right there. That's what a full cycle in the HIP, what the material would look like. The experiment here is to look at, well, what happens if we interrupt the HIP cycle? Because what we want to know is, well, how does our chemistry behave? How does our phase formation occur? But also, what's the what mechanistically is happening as the can is being deformed and pressed? So what this nicely illustrates, you can see there's a clear transition between 850 and 950 degrees Celsius here, where we don't have any material forming on the surface. So that's when we've got a nice durable waste form. Below that, you can see some phosphate coming out of the material, so we've got leachability in the material. So we just haven't quite got the material properties we require by that point. This also feeds into our safety cases. So by knowing what's happening at every point in the profile, we can design how the HIP profile works. The HIP's installed within a hot cell, so that we know what the failure mechanism is at the different points in the HIP cycle and what we need to protect against in each of those points in the HIP cycle. So it's a very neat and simple illustrative bit of work that we've done there. I guess the other point is we need to scale that up to something of a reasonable scale. So for the Symo facility, we're making cans that start out at about 30 litres in volume. They're pressed down to about 15, 16 litres. And we'll run many years ago, we went through a full scale-up process on that. So the can you see in the middle there, the large one with 4, that's what a package coming out of the Symo facility will essentially look like. The size of the can, I'll just go back to the size of the can. It's driven more around operational constraints of the site, less around the optimal size for the facility. And that's the nature of any design of this type of process. You're typically driven by where that material is going as opposed to what's the most ideal for what you would like to do. So the facility itself, jumping away from some of the development work and moving into the actual facility, I guess the point I'll make here is we've had handover of the building from the builder, and it's been handed over to the project now. So we've moved from a construction of the building phase into a process installation phase. So these pictures give you a little bit of an idea of the scale of the facility. What you can see basically the hot cells themselves. So the hot cells, the process hot cell is about 12 or 13 metres high. The HIP hot cell is about 10 metres high. The length of the hot cells is about 30 or 40 metres. It's a big facility. A lot of the systems that we have in place already are the backbone of the active ventilation systems, which you can see the ductwork and pipework sitting on the side of the cell there at the moment. So that's waiting for us to integrate our in-cell components of that into that machine. We have a number of the liquid systems installed in the facility, so where our additives come in, where our cleaning solutions come in, where our waste comes in. And we also have our off-gas plant fairly well complete, waiting for us to connect up to. But we have a lot of other systems that have been built outside the facility that are ready for install. And the way we've approached it is to build modules or units, finish those modules and units outside or in workshops, and then integrate and bring those into the facility. So we're making reasonable progress towards having stuff installed. A lot of the other equipment might be approaching that being ready for installation. So just an idea here, we have a fairly large conveying system in the cells to move our can around. Once we fill that can, we need to move it to evacuation and sealing. We need to move it to our HIP. So that process is done on a roller conveyor with those destinations and movements on the conveyor being controlled by being automated. And we have our evacuation and welding system on the right-hand side there. The HIP system itself, the HIP is a very large and impressive piece of equipment. So Quintus from Sweden have supplied the hot isostatic press. To give you an idea, the height of the press is about 6.5 metres. So this is really the first industrial large-scale implementation of a HIP in a hot cell in the world. There's been small research HIPs in hot cells previously, but they're really babies by any comparison. A lot of the challenge of the press itself is automating the loading of the can into the HIP, automating some of the, or the maintenance of the HIP as well. That's why what the robot is there for. It helps with furnace maintenance, removal of components of the HIP from the facility. The press itself is fairly large. The pressure vessel is probably about 12 to 1300 mil by maybe 600 or 700 mil in diameter. So it's a large press. So that machine's at ANSTO at the moment. The hot cell's being prepared for it to be installed. The installation of that will be the full-blown installation of that will be starting after the start of the new financial year. So Quintus will be coming out from Sweden and will be working with us to install that machine. So they could be here for 2 or 3 months with us getting that machine installed. I'm going to just make a jump back to talking about I've talked a little bit about automation and some of the nuclear automation that we've been working with. This probably demonstrates a lot of the value of the demonstration plant. We use that facility to develop the architecture for the control system of SIMO. We developed it, we tested it, we've written all the software manuals, a lot of the code, the blocks ourselves. We've tested it in that facility, we understand how it works. There's a clear focus on safety, how the process behaves so making sure the process always trips to a safe state for maintenance, and that's been one of the philosophies of how we've designed this. But we're responsible for the design, delivery and integration of that. I guess you can see some of the numbers on the right hand side there. They start to get a little bit intimidating, but it's large. But it's achievable. We have, and we're working through the development of this at the moment. So the image below is actually the control room in the demonstration plant, and that's basically mimicking some of this, what the system will look like in the final facility. So there's probably double that in the control room in the final facility or more, but we're making sure that we're educating people on what we're showing, so we're not showing traditional P&I views, we're showing system performance views. We've got a lot of trending and tracking. It's about situational awareness, giving the operator the information they need to understand what state their plant's in. So there's been a lot of effort and development in that, and it will be a very robust, but also very clean. So I guess just to give a little bit of a closeout on where we are on the facility. So as I said earlier, we've had that handover. of the building to us. We're now getting into that installation phase. We're moving ahead with that. It's been a slow start, but we're really building on that. The middle part of this year is going to be incredibly hectic. We'll move into cold commissioning later, sort of in 2023, and then the target on hot commissioning is in 2025. And most importantly, then moving into that translation to a full operational, reliable facility, which happens after that.